Good morning. My name is Nick Brisbois. I'm a Senior Applications Engineer here at Biamp Systems, and today we're going to be doing a presentation on the TesiraXEL Amplifiers and with regards to sound reinforcement. First thing I'd like to do is just make sure everybody can hear me. On the right-hand side of your screen, you've got an option to raise your hand. If you can hear me, please do so, just so I can see that folks are listening. Great. Okay, I'm seeing a whole bunch of those come up. So we'll get underway. Okay. Topics we're going to look at today, we'll take a look at the overview of the hardware, just in case anyone is unfamiliar with the amplifier. We'll kind of get our feet on the ground with that. Then we'll take a look at the asymmetrical power allocation options for the amplifier, sleep and mute versus GPIO, auto locate and delay EQ within the amplifier. Then we'll dive into the TesiraXEL and community loudspeaker processing libraries. And look at how to determine the right amount of power for amplifiers with various speakers. We'll take a deep dive into limiting, and we'll get into network topologies for signal path redundancy, very important for live events, and take a look at network security as well with 802.1x. So the TesiraXEL amplifiers, we have two models available, the 1200.1 and the 1200.2. They both have a 1200 watt module in those. The 1200.1 has a single 1200 watt module. The 1200.2 has a pair of them. So in the 1200.1, we've got 1200 watts across 4 channels. In the 1200.2, we've got 1200 watts across 2 channels, and then another 1200 watts across 2 channels for a total chassis power of 2400 watts. And on both of those, they're non-bridging outputs. So the 1200 watts is the peak you can get out of any one channel. Some of the unique features of TesiraXEL, the asymmetrical power banks, where we can assign power to any channel in any mount, up to 1200 watts. The per channel delay EQ group assignment, so we can treat each output as an independent zone within your building. We've got an integrated 2-port AVB switch in the device. Redundant AVB can be done with this device. We've got a daisy chain connection mode. We support rapid spanning tree protocol, or RSTP. We support 802.1x across the platform. We can do audible locate channel IDs. We have GPIO, which can trigger sleep and chassis mute, and we can go into standby. So we'll take a look at those functions a little deeper. Here's the Excel control block. This is where we set up the functions of the amplifier. On the left, you see we've got some auto mute functions. So if we stay below a given threshold level for a certain amount of time, the amp will mute itself. It won't power off. The recovery time is just a few milliseconds to come back from that. We've got channel power settings. You can see here we've got selected 250 watts on one channel, 500 on another, 200 on another, 200 on another. And we've got a variety of output loads on this, 8 ohm and 70 volt. And we can mix and match those across the chassis. And then we've got an output tab as well, where we've got control where we can toggle between dBFS and dBu on our metering. We get some information on various protect modes as well. Just a few more options. One of the things we can do here, we can trigger also enable the fault LEDs. So this allows us to determine if we want to show, if we know that we've got, for instance, a 70 volt system, and we know that occasionally we will overdrive it a little bit, and we expect to see kind of an impedance warning, but we know it's not a problematic one, we can suppress that fault so the customer's not seeing a red flashing light on the front of the device every time a page is made. The rear panel of the devices, we've got the 1200.2 on the top and the 1200.1 on the bottom. They look just about the same. They've got a little different in screen printing, but that's about it. We've got our GPIO connector on the back, break it out here. It's labeled with the default pin functions. By default, it is set to support a sleep mode on pin 3 and a mute all on pin 1. So we can tie that into external control panels to trigger a mute on the chassis, and this goes across all channels. So when it's shorted, we go to mute. When it's open, so no connection plugged into it, audio passes as normal. We can also drive a momentary 5-volt input to sleep and wake the amplifier. The 5-volt LED or 5-volt logic trigger from the port goes to sleep with the amplifier, so we can't self-power this circuit, so you'd need an external 5-volt power supply to power that up. Output connectors. As I mentioned, we've got the asymmetry in this amplifier, so these can be configured to any power level that you want across the 1200.1 and in banks of 2 across the 1200.2. So if I'd like channel 1 to be 1200 watts output and channel 2 to be nothing, I can do that. If I want 600 and 600, I can do it. If I want 900, 300, 800 and 200 and leave some in reserve, I can do that. So we're very flexible in what we can do. The one thing we cannot do is bridge channels. So we support 8 ohm and 4 ohm operation, 70 volt and 100 volt operation. We don't go down to 2 ohms. So for that, we would need a different architecture. TesiraXEL supports some basic impedance monitoring. This is for amp protection under unexpected load conditions, and then it will flag in the faults that it is detecting something out of the expected range. This is not intended for line monitoring. It's not intended for speaker driver monitoring. We don't have that functionality built into the amplifier. We can see sort of basic faults, but we can't profile a system and store snapshots and go back and redo that again. If we do detect faults, we can either always notify via front panel LED and system fault warnings, or we can suppress those with this. If they're suppressed, they still get logged in the event log, so you can pull the text event log out of the device and see if you've been seeing impedance faults, but the user isn't aware of those happening. They're not going to be calling for a service call because they see a blinking red light. The front panel of the amplifiers, take a little tour of these. Looks like a normal Tesira interface. One important thing, there's no OLED display on this. So everything is just the LED indicators. Audible locate feature. This gives a text message from the device. When you press that, it'll cycle through. You can see the lights indicating the channel that it's cycling through there, 1, 2, 3, and 4, and it'll say audible locate channel 1, audible locate channel 2. This allows you to quickly just verify that the wiring, you don't need this to be a configured system or programmed system. It'll just run in the background while you have it active. It allows you to verify wiring for all your speakers. It also will identify the amplifier within Tesira software when you're running this. We've got channel mute by front panel selection. We also have a mute all function for all 4 channels. If you were to have channel 1 and 3 muted and then hit mute all, 2 and 4 will also mute. When you undo mute all channels will unmute. We have a sleep button on the front. This is basically a power on-off button. We call it sleep because we don't go to a full 0 power draw. We're still powering up the GPIO ports on the back so we can do a remote wake. So we need just a couple of watts of power being drawn by the device to keep that alive. Chassis sleep from the rear panel. Once it's gone to sleep, it goes off the network. We've powered down the network ports, we've powered down everything. You do get a warning in Tesira if you try to open the amplifier block, but it is the system is aware of it, so there are not system faults being thrown or anything like that. The device is in a sleep mode. It warns you that it's currently sleeping and it's not available. Once the amp is woken up again, you can click and open the block. The front panel functionality also can be locked out. You can press and hold 2 of the mute buttons to do this, or you can do it within software to lock out front panel access to prevent people accidentally shutting the amp down or muting channels. Okay, delay EQ groups. So within Tesira software, we have the idea of delay EQ. And this is where we can take inputs for, if we've got multiple rooms, we've got all the inputs within a room, get time aligned through the system and play out at the same time at the far end. So we don't want to see a source being delayed because we have more processing happening on mic number 3 than on mic number 1. We don't want to have lag on mic number 3 versus number 1. We will timestamp them and play them all out, accounting for the processing path length difference. So everything plays out in time alignment. The unique feature of the XCEL is that on each output channel, we can drive a different delay EQ group. So by default, it is all one channel, all one delay EQ group, and you can choose which one. Or you can choose per channel delay EQ group and choose a different group, and you can create user groups as well. So if you've got a complex installation, you can maintain path lengths for different rooms isolated from each other. And this can be in large systems can be important for kind of managing overall DSP usage. All right, we'll get into the Tesira processing library now. We've kind of done a speedy overview of the amplifier hardware, the delay EQ groups. The Tesira processing library is something where this is a really nice feature of this amp. So we have a couple of options in this. We have the community professional loudspeaker processing library, and we've got basically their full lineup of speakers, and you can just drag and drop processing blocks in by model, and it will put the factory presets into your Tesira program. So you don't have to go look up the data sheet, type those in. You just drag and drop, it's already in. You'll notice the title, the name of the catalog, is in the kind of a dim gray. If you create your own catalog, it'll be a white title. These are preloaded with the Tesira software. So when you install your software, these come along for the ride. Next thing we have is the Biamp TesiraXEL blocks. So this is a drag and drop library that has got some layouts that are effectively multi-way processing layouts. They are done in a way that's similar to a fixed chain DSP. When you used to have your standalone speaker processor in the rack, this is going to take the place of that, and we'll just do it within the Tesira. So here's a couple of examples of it. On the top, we've got a 1200.2 amplifier running in a stereo pair of two-way crossover pairs. In the middle of the screen, we've got a 1200.2 layout where we've got it just broken out as 4 straight through connections. We don't have any crossover on it. And the bottom one, we've got a 4-way crossover installed. And I'm going to pull the Tesira software over here so we can take a look at this for a moment. So if we go into the menu on the left here, we'll see we've got our processing objects. And here is a amplifier being dragged into the software. So we can pull some pretty complex layouts right into the software. Elements that you'll need to tune yourself will include your crossover frequency and slopes. Any PEQ that you need to do on a per element basis. If you need delay EQ within to offset a driver, you can do it there. Peak limiter for driver protection. And then we've got a peak limiter for the AVB hop, and we'll get into this later why we have that as an independent thing. And finally, the amplifier chassis over here. Within the amp chassis, as mentioned, we can set up our auto timeout. We can disable it or set it in 15-minute increments up to an hour. An input level for the amplifier. We can invert the signal. We can set our power range. So we can do it either through the toggle up and down. We can type in a value. Oops. And it will apply it down here. We also have control handles down here that we can drag and change those channel values in real time. So if I want to say that that's going to be full power, or I can choose any of these to be my large channel, other ones to be the small channels. So we can do it in any mix and match combination. You can assign these as 4, 8, 70 volt, and 100 volt. When we drop them in as 70 volt or 100 volt, we'll put in a high pass automatically. You can defeat that if you want to, but we put it in by default. And you've got your enable fault LEDs here. You see 2 are grayed out. That's because there's no power allocated to those. Once we go below, I think 10 watts, we disable it because we can't get an accurate reading at that point. On the control tab, this is your output volume for the amplifier channel. We can scroll this up and down. We can look at power in dBu, which is the traditional metering in Tesira, and these are RMS levels, or dB full scale. And so since we're in a digital environment, we can look at that full scale. The difference is the notation on the left. The meter will continue reading in the exact same spot. It doesn't matter which notation you're using. What is important to know is 0 dBu is equal to minus 24 dBFS. So we'll see that populate in a live amplifier. We have a clip indicator light at the top of each channel. We've got limiter indications, protect indications, and fault indications. And this field down at the very bottom here is a scrolling message tab. So as any amplifier faults or warnings come up, you'll get a scrolling text log through there that show them. They'll also be entered into the event logs. And on the output side here, we've got a logic output for faults and warnings, and this has been tied to a labeled logic block. So if you want to connect it to a control panel in Canvas or something like that, you can simply copy paste it right in. As mentioned, we've got this for a few different layouts. So kind of the most common 2x2, a 3x1, 4-way. We've got an amp just with a limiter already preset. So the 28 dBFS or 28 dBu max is a peak voltage. We'll take a look at that a little bit later in the webinar here. This is the peak threshold, and we'll see that RMS, that's going to be 25 dBu RMS with a 3 dB crest factor. That 28 dBu is 0 dBFS. So if we exceed 0 dBFS, then we get into digital clipping. Digital clipping is bad. We'll have a look at what it looks like, but introduces a lot of artifacts and things we don't want to see. So we've got all those as drag and drop options for the amplifier. We've also got just some generic speaker processing blocks that can be dropped in. These can be exploded. They've got logic connections for mute and other states. So these are just handy building blocks for doing systems. As mentioned, we've got the community options here. These are pre-populated from the factory. An FIR filter, we can only bypass. You can't see what the filter is doing. Parametrics, level control. So these are, as I mentioned, pre-populated. So you just choose your model, grab and drag, and you're ready to go. We also have the DeSono loudspeakers, the ceiling application for conference rooms. So we won't get into that today. And one other thing I'll quickly show. If you're looking to add an amplifier, you come in to the amplifiers tab. It'll give you the TesiraXEL 1200, and then you can choose the 1201 or 1200.2 in the drop downs. Our GPIO on the back panel, it can either be used for the sleep mode and mute override, or we can defeat it and just use it as a standard GPIO. And if you don't want those logic output nodes showing the fault states, you can defeat that as well. All right, so we'll get into some power questions. So how much power do we need? This is kind of the key question. If you've got an asymmetrical power amplifier that you can define the output channel per or output power per channel, next thing we need to know is how much power are we going to use? Well, we need to know a few things about the site to do this. We're going to need to know how far the listeners are from the loudspeakers. Could be a conference room application or background music in a building where we're doing ceiling speakers and listeners are 5 or 6 feet from the speaker. It might be in a performance space where people are 30 feet away from the speakers, 50 feet away from the speakers. We need to know the target volume. Is it background music at 70 dB? Is it a live music event at 95 dB? Where's our target? We also need to know the program Crest Factor. What kind of headroom do we need? We've got the RMS value, but then we're going to have peaks that happen. And so we need to plan for those peaks so that we're not clipping the amplifier when we get to the peaks. We can use limiters to help to cap excessive peaking. We can say, okay, we're expecting 12 dB of headroom, and we can put a limiter in to stop anything that goes beyond that. But we want to know kind of what our program type is going to be so we can plan for this. The next thing we've got is our loudspeaker sensitivity rating. This is for an amount of energy that we feed into the speaker. How loud will it be? Fortunately, these are all things that are normally published in the data sheet, so we can look at a data sheet to see what it shows us. At support.biamp.com, we have a calculator, the Amplifier Power calculator, which is really handy because you can just type these numbers in and it'll give you the required amplifier power and RMS and peak as an output value. So this will tell you how to set your power bank. So we can grab a browser here and take a quick look at this. So this is the support.biamp.com page. In our design tools, used to be called calculators, but we've expanded it, so now it's design tools, the Amplifier Power calculator. And here we can define our speaker sensitivity. Typically they're measured at 1 watt at 1 meter. So we can put in a sensitivity rating. So we've got a horn compression driver that's got 100 dB SPL rating. Distance to the listener position, say 20 feet. Volume at the listener position, say 90 dB. And headroom, by default we're at 12, we can say 15. And it will give us the values that we need for our amplifier. So it's a very quick and easy way to kind of do your initial legwork on setting up the values. I'm going to look at kind of power scaling because we're looking at those values. Loudspeakers, here at the top of the screen, we can see sample loudspeaker sensitivity 90 dB for 1 watt, 1 meter. This might be common for like a ceiling speaker for conference space. Something that's a direct radiating speaker. So something that's, your bookshelf speaker where it's mounted flush to the front of the box. If you do horn loading, you get some efficiencies due to the horn. And so the rating you'll get 95 dB or 98 dB or 100 dB. But we'll start with a 90 dB speaker. Powered at 1 watt, you'll get 90 dB SPL at 1 meter. You can see down here at the bottom left, twice the power is 3 dB. 4 times the power, 6 dB. 10 times the power gives you 10 dB. So if we jump from a 1 watt amp to a 10 watt amp, we're increasing 10 times the power. So we get 10 dB SPL out of that speaker. If we go to a 100 watt amp from 10 watts, we've gone another 10 times the power. So we've added 10 dB SPL more. If we go to a 1,000 watt amp from the 100 watt amp, we've added 10 dB more. So we're at 120 dB SPL. The maximum for your amp is going to be that's going to depend on the power rating for your loudspeaker. So we've got the sensitivity, which is how much sound does it produce for 1 watt in, and then we can scale that up. But we also need to know what's the maximum amount of power that that speaker can handle. It may be that 1,000 watts is far too much, and that speaker will tear itself to bits before it can get to 120 dB SPL. It might be perfectly happy on a 100-watt amplifier. So that's an important value to know. Here's another look at it, and we're scaling differently. This time we're doing, instead of doing the 10 times power per jump, we'll do the 10 times per power to get from 1 to 100 watts on that first hop there. But then the next step we're going to do is a 3 dB boost. So we're doubling the amp power. So 100 watts to 200 watts, we get 3 dB louder. 200 watts to 400 watts adds another 3 dB to our system. If we were to go 400 to 800, it would go up to 119. 800 to 1600, we'd go from 119 to 122. In terms of what we perceive as twice as loud, somewhere between 6 and 10 dB is what we would perceive as sounding twice as loud. So kind of gives you an idea of what that difference is. When we're looking at power, we've got two ways to express it. One is when we're talking about the electrical energy, that is done with logarithmic scale using base 10. When we're in a field environment, like a free field speaker enclosure, we use log base 20. So it's twice the value. Here we're looking at kind of sound radiating out. We talk about free field acoustic energy and losing 6 dB per doubling of distance. Well, what's happening in the perfect environment? We've got a point source playing out into infinite space. So that little teeny point source plays out an infinitely loud volume, and it expands in a perfect sphere around it, moving air molecules further. And as it propagates out, air molecules are jiggling, and that energy becomes dispersed. As that sphere gets bigger and bigger, the amount of energy remains the same or starts to diminish due to heat loss, but it has to affect more and more area. So distance 1, so we're showing down here distance 1, so we've got a sphere of with a radius of 1. We can plug it in. Our equation for the area of a sphere is 4 pi r squared. 4 pi times 1 squared is 1. So 4 times 3.14 times 1 gives us an area of 12.56. If we double the size of that sphere, we blow up the balloon twice as big, we go from 1 to 2 for our radius. 2 squared is 4, and we can multiply that out. So the surface area is 4 times larger than it was for the radius of 1. So we've got 4 times as much surface area to energize with that same amount of energy that we had at 1. So it's louder. If you're standing at position 1, it's going to be louder than at position 2 because the energy is being distributed around more of the environment in position 2. And if I double that again to 4 units away, it'll be 4 times more, and we'll reduce our volume even more. So the way that's expressed typically is we see a 6 dB loss per doubling of distance in a free field perfect environment. If we go indoors and we have reflections off walls and things like that, it'll be less because we'll have the perceived energy of the late reflections making it sound louder. So that gives us kind of the theoretical background of like what's happening is this energy. We put all the energy into the speaker. Now we're going to distribute it around the space. Where does it go? And so when we talk about a 6 dB loss, this is where we're talking about it. So every time we get twice as far. So let's put an RTA out there, a SPL meter out in front of it, and we'll power up a little horn driver. It's got a sensitivity of 100 dB at 1 watt with 1 meter. We'll power it off a 1200 watt amp. And at 1 meter, we're going to hear 132 dB SPL. If we go 2 meters away, we're going to be down 6 dB. 4 meters away will be another 6 dB, so we'll be down 12. Double it again. Another 6 dB at 8 meters, so we're minus 18 at 8 meters. So the SPL reading at 8 meters, 25 feet away roughly, is going to be 18 dB less than at 1 meter. So if I go from somebody with their head right at the speaker to somebody 25 feet away, we'll lose 18 dB just because of the propagation through air as it spreads around. And if we double our distance again out to 16 meters or 50 feet roughly, we lose 6 dB more. So our loss from position 1 to 2 and then 2 to 3 is quite a bit more here. We've got 18 dB of loss for this jump, only 6 dB of loss for this jump because we're doubling the distance once here. We've doubled the distance 4 times here. All right, we're going to take a look at crest factors in program material now. I just grabbed a couple of files in Audacity and sampled them. And what we're looking at here is a clip, just a generic song. At the top of the scale, we've got 0 dBu or 0 dBFS. So that is our peak. That's the normalized playout. It's probably within 1/10 of a dB or so of clipping for playout on Apple iTunes or whatever it is. That's the peak. So if we were to set an amplifier up to say, okay, we're going to play out peak output is 1200 watts. Well, that's as loud as it's going to get. So that's our 1200 watt peak. It's our digital 0. The amplifier maxes out at that. And then we can look at this song and just say, okay, where does our energy, where's the RMS energy of this music? I guesstimated it to be about -15 based on this. So we're going to say it has a crest factor of 15 dB. So the peaks crest 15 dB higher than the RMS value. So most of the stuff is happening down around that RMS line, but snare drum hits go up to the peak. Certain things will go up much higher, but your average is about -15. Now we talked about the scaling. For every 10-fold increase for 10 times the power of the amplifier, we get a 10 dB increase. So we can look at our scale and say, okay, we've got 0 at our peak, 10 dB down is going to be 1/10 of the amplifier power. So 10 dB down, we are at 120 watts. 15 dB down, well, 20 dB down, we can go 1/10 again. So we're down to 12 watts down here. Somewhere in the middle is going to be our 15 watts. So say 60 watts is going to get us the RMS for this. So 60 watts RMS, 50 watts RMS will give us our crest factor. Now we would have to apply that to our speaker and look at the sensitivity of the speaker to find out how loud that speaker is going to play out in the space. If I've got a very inefficient speaker, it's going to be quieter than a very efficient one. So something, a horn-loaded driver is going to be more efficient. It's going to put out more acoustic energy for a watt into it than a ceiling speaker, which is can be fairly inefficient. So we can gain power by choosing the right driver. You can look at the sensitivity ratings of 2 different products and say, oh, I get it. I see a 3 dB difference in the sensitivity rating. Well, that's a free doubling of power. 3 dB is double the power. You can double your power just by choosing one product over the other. So it's an important thing to know. It's typically cheaper than buying amplifiers. So we're going to stay on this same song. We'll look at kind of peak SPL now. If we say, okay, that 1200 watts translates into 106 dB at, I think I was using my earlier example at, let's take a look here. Yeah, roughly 1200 watts at 100, 106 dB at the 50-foot mark. So 50 feet away, we're getting 106 watt or 106 dB peaks. Our RMS value at 50 feet away is going to be down around 90. So you can determine then, is that loud enough for the performance space that you're in? You've got a couple of options at that point. You could choose a louder or a more powerful amplifier, a speaker with higher sensitivity, or you introduce delays. So if 50 feet is, you're not getting the sound pressure level that you need at 50 feet, you can put a second set of speakers at 40 feet that are reinforcing and giving us more SPL. Here we can look at the output voltage of the amplifier. We can look at it in watts. Some amplifier or some speaker manufacturers will look at the volts being applied to the driver. For 1200 watts into 8 ohms, we'll get 96 volts peak. Your average, 3 volts for RMS. So it's a fraction of it. And then finally, we'll look at the 3 dB changes here. So 1200 watts, 3 dB down, we're at 600 watts. Another 3 dB down, -6, we only need 300 watts. 3 dB down to 9, -9 is 150 watts. Another 3 dB down to -12, we're at 75 watts. Another 3 dB down to -15, and we're drawing 37.5 watts RMS. So that crest factor kind of illustrates where the differential is. If we were to have a shallower crest factor of 9 dB, we would need, if our crest factor, if we were doing highly compressed music and we needed our RMS level to be sitting up here at -9, we'd need 150 watts instead of 35 or 40. Here's another song. This has got a much higher crest factor, so the RMS value is much lower. So in the previous example, RMS is -15. Here, RMS is floating down at -23-ish. It kind of cheated the scale because I had one that didn't reproduce properly. So this is a Depeche Mode song, and one, they're not cresting as high. The peaks are coming in at -3 instead of at 0. So already it's 3 dB lower on the peaks. We're also 8 dB lower on the RMS value. So this song is going to be 8 dB quieter than the other song, and that's just the mix. So your peaks, your snare drum hits are almost as loud. They're 3 dB quieter, but the average level of the song is going to be 8 dB quieter than the previous song. So it's about 5 dB quieter. The mix overall is about 5 dB quieter than the previous song. So there we see that one at -15 and this one -22, -23. And here's another one. This is another that comes in with about -15. And I might be a little bit low on this one. It was sort of the troughs. I kind of cheated the RMS down. It might be closer to -12 RMS. So you'd have a 12 dB crest factor. And so your required output power would be a bit higher. So you can see how the program material can dictate sort of what your RMS power out of your amplifier is going to be. The RMS power matters because that's going to be your average duty cycle for the amplifier. What can you maintain? And the TesiraXEL, we've got very good results with testing on our power supplies, and so we really don't have any caveats in terms of program material. If you're going to, we won't sustain a 1200 watt sine wave indefinitely, but program material, you're going to be able to play a program all day. So how much power is needed? As we mentioned, we can look at the specifications, the sensitivity, and the power handling of the speaker. There's two ways that can be phrased. Certain manufacturers will give it as 1 watt at 1 meter. So for 1 watt of input power at 1 meter, we'll expect 98 dB or whatever it may be. Others will give it as a voltage. So they'll say for 2.83 volts input, which equates to 1 watt for an 8 ohm speaker, we'd expect to get 98 dB. It should be the same for the two values. This will give you roughly the ability to start honing in on your target SPLs. There's going to be more modeling of the room with respect to how the speaker itself covers, what its coverage pattern is and things like that. But this gives you a rough working starting point. Knowing the crest factor of the content is really important, as we mentioned, because that's going to determine your power handling numbers. And again, the online amp calculator is really handy. So we can plug in our numbers on that calculator tool and say, okay, I've got a speaker that is rated for 100 dB SPL at 1 meter. I'm going to be 16 meters to the audience position. That was the 50-foot position. And my average RMS out there is going to be almost 92 dB. And I'm going to have 15 dB crest factor. So my headroom is going to be 15 dB. So we're going from 91, and the crest factor would allow a peak volume out at the listener of 106.7. And the required amp power is 38 watts continuous and 1200 for those peaks to get the 15 dB. When we look at the data sheets for speakers, they'll specify, as I said, in watts or volts, that RMS power handling capacity. Generally, they may give an instantaneous. They should give a long-term average for pro speakers. They'll also give like an infinite duration test. We're not really interested in the infinite one. We want the kind of average one. A lot of companies have done 2-hour windows, but what it allows it to do is heat up the loudspeaker's voice coil, get everything to where power compression starts to set on within the device. As it gets hotter, resistance changes, and so it affects the how the voice coil magnet operates in terms of what the amplifier can do to it. They then apply pink noise with a 6 dB crest factor, so it's been limited, so it's got a 6 dB crest factor, and band passed from about 40 hertz up to 5K. And then they run the speaker at that as loud as they can and see where it fails. And they back it down, and when they get one that doesn't fail, then they say, okay, now we're in the ballpark, and that becomes the power handling for that speaker. So it's got pink noise with a 6 dB crest factor. Amplifiers generally are specified with sine wave, which has a 3 dB crest factor. So we're looking at a 6 dB crest factor on one and a 3 dB crest factor on the other. So if you add 3 dB more to get to that peak, you can sort of say, okay, we need an amplifier who's got twice the rated power of the speaker, and we should be safe. The maximum SPL on that speaker is going to depend both on the speaker and on the signal. So something with a really high crest factor is going to end up with a lower RMS value, because we saw that crest factor, if we've got a really, the snare drum hits are much louder than all the singing. Well, your singing is the RMS value. The snare drum hits are the crest factor. So if we've got 15 dB of crest or 22 dB of crest, your RMS value is pulled down. You can artificially boost it by adding limiting on the top end to squash that snare drum hit so it's not as loud relative to the singing and raise your RMS levels. Here we'll look at a couple of spec sheets really quick for a couple of the community products. This is a horn-loaded driver, and we can look at the max input ratings: 200 watts continuous, 500 watts program. So continuous being basically the RMS long-term, program twice that. So that's kind of your 6 dB crest factor. Or sorry, that's a 3 dB jump, and then 6 dB would be up to 800 to 1,000 watts for momentary, which is shown by this 89 volts momentary peak. We saw a moment ago, if we scroll back to this slide, 96 dB or 96 volts was 1,200 watts. 89 is going to be sort of in the 1,000-ish range. And we can see here it shows the low frequency sensitivity is 102 dB at 1 watt. Mid-high sensitivity is 110 dB. So it's more efficient than the low frequency. Another model, the Community R1, They state theirs at 160 dB sensitivity at 2.83 volts. So same product line, two different ways of specifying. So a lot of times that just has to do with who's on the project team when it's released. A subwoofer, a little different sensitivity rating. Here we're at 97 dB, and it's band passed. So that is applicable just within that range. And we see a 400 watt continuous 1000 watt program. So, and again, 80 volts as your momentary peaks. So you can see what's the max allowed peak on that device. How much power is needed? As we mentioned, the rule of thumb, recommend an amp that gives peak power 3 dB higher than the noise rating for the amplifier or for the loudspeaker, because the sine waves have a crest factor of 3, pink noise has a crest factor of 6, and we want to bring those into alignment. Speaker at 150 watts average pink noise rating would need 300 watts to drive that without clipping. And that's going to be variable depending on what you're doing with limiting, what your RMS level is, and what your crest factor is. So let's, as with many things in audio, it's not a set in stone number. 70 volt and 100 volt systems. So we've been dealing with 8 ohm, 4 ohm. When we jump into the 70 volt, 100 volt systems, it's a little different because we drive the components differently. 70 volt, 100 volt refers to the maximum output voltage for the amplifier in that mode. North America, we're typically on 70 volt systems, other countries, 100 volt. We're seeing some systems that are 140 volt for driving really large speaker configurations. If we're doing football stadiums, if we're doing racetracks, things like that, where we've got to drive, a kilometer of cable, you might need a higher voltage rating. Every speaker in that system is going to have a transformer, which is going to step down the voltage that's coming down the line, and so it brings the voltage down and turns the current up. So we can drive the energy to do the drive the magnets within the device. And those transformers at the speaker usually have one or more taps, which are, they've got the primary winding, and then they've got the secondary windings, which resonate with the primary and give you the whatever your various step down ratings are. It can be a step up or a step down transformer. You're stepping down from high voltage to low voltage. And these taps typically will have increments either in the 1.5 or 3 dB increments. And they do this so that you can balance the output level of the speaker. So if you're doing an installation, you've got a speaker that's, you've got to place one a little bit farther away than anticipated from all the rest. You can boost it up by 3 dB by just moving it to a different tap position, and your listening level in the audience area remains constant as they move back and forth between those speaker zones. So it's an easy way to modify them in the field. This is one reason that it's generally recommended to leave 10 to 20% headroom in your amplifier calculations, just in case those kind of variations are made. It also is just variations in manufacturing, things like that. And those speakers for 70 volt and 100 volt can go from very low, 1 watt a piece or even less, all the way up to 100 watts and more with transformers. So the amplifier power is going to determine the number of speakers that can be attached. You sum the total number of, or the total wattage of the speakers being driven. They don't have to match across all the speakers. I could do some at 20 watts and some at 10 watts, but my overall number, the summation of all those, the 20 plus 20 plus 10 plus 10, needs to come up to less than the total output power of the amplifier. So 2 ways of calculating it. You could say, okay, I'm going to start with the number of speakers. I'm going to power 15 speakers tapped at 10 watts each. I'll need 150 watts. Then I've got to add that headroom to it. So 15 to 30 watts would give me an amplifier of 165 to 180 watts. So that's one way to do it. The other way would be to start with your known amplifier power and say, okay, how many speakers can I put on that? And it's going to be, if I've got a 250 watt amplifier and I want to reserve 20% of that would be 50 watts, 10% would be 25 watts. I'll have 200 watts available for the speakers. Now I can just divide that up by the draw of the speakers. So I think it's faster to work from the amplifier power down, but in some applications you have to work the other way. There was a question asking if we have support for 48 volt or 25 volt in this, and currently no. You know, you can always send, if you have requests and things where it is, you've got a product that you're needing, please send us the details at support@biamp.com. We'll forward it on to our project management, our product management teams for evaluation, because you know, we're here to build the stuff that you need. Here's a quick look at how voltage, power in watts, and loudness kind of interrelate. We've got the change in dB on the left. 3 dB change needs twice the power. So we go from 300 watts to 600 watts, or from 500 watts to 1,000 watts, or 10,000 watts to 20,000 watts. Any of those will give you a 3 dB change. Your voltage is doubling every 6 dB. And your loudness is doubling every 10. So 10 times the volume, perceived volume, is twice as loud. Or sorry, 10 times the 10 dB is twice as loud in the perceived volume. So what causes speakers to fail? Typically, this is going to be an issue of kind of a combination of things. You're either dumping way too much power into them, and so the speaker bottoms out and just gets crushed in the voice coil. You might have a magnet that shorts across the voice coil. Often that'll happen if there's clipping. It's trying to start and stop the motor very quickly, and it can cause it to arc and disintegrate. Too much power can cause things to just straight up melt in crossovers and things like that. But also too little power, if you're driving an underpowered amp, and so it's constantly driving into clip, you're going to get weird harmonics through the system. You're going to get irregularities in, instead of a nice push-pull method, it's a jackhammer type method, and that is just going to destroy the driver. So there's a number of things that can cause those to fail over time. So getting into limiters and clipping, and hopefully we will, we'll jump right into this. Some of the benefits of limiting. Gives you a safety valve for the system. Basically, it makes it dummy proof. If you're gonna, somebody accidentally boosts the 500 hertz EQ by 12 dB, or pushes a fader way up, it acts as a kind of a backstop against that just being passed right onto your speakers. When properly tuned for bandpass, that's you've got a low frequency driver, a mid frequency driver, and a high frequency, and they're done off of a crossover. You're tuning them for the bandpass. It can help to prevent distortion within those. It prevents clipping of the next device in the signal chain. So I'm sending audio from device 1 to device 2. If I send the audio coming out of device 1 exceeds the input capability of device 2, I can clip that. In an analog environment. In digital environment, I'm going to actually clip the signal going over the digital pathway. Limiters also prevent high frequency component damage due to harmonics and the distortion, and we'll take a look at those in a second. Some negatives of limiter: it can cause your sound to be really just dull and over compressed. If you just artificially squash it too much, set your threshold too low, or a release time that just multi-second release time that it never lets go, or it can cause amplifier or speaker to overheat due to limiting that dynamic range also. So you're taking what was a program material 15 dB of crest factor, and you're just squashing it, and you just take your crest factor down to nothing. Well, now you've basically got just a sine wave. So that can cause things to get overheated. One of the things that I always like to do is put limiters at the edges of my devices. Within, I'm supposed to be clipping at the top there. Within the Tesira DSP, within most DSPs, within digital audio workstations, Pro Tools, things like that, we use floating point notation. And it's essentially, it's a mathematical notation that allows you to scale things radically. It works very well with audio program where you need very quiet fidelity at very quiet levels, but also fidelity at very loud levels. And it allows us effectively infinite headroom. You can build a signal chain within Tesira and run it up to plus 600 dB. And as long as you bring it back down to 0 dBu on the output, it'll come out and sound just fine. It's not destructive. At the output, we're going through either a D to A converter to an analog output or a D to D converter to AVB, to Dante, to Cobranet. But it's going to transition from that floating point math value to a fixed point math value. And that's got a maximum threshold. It's got an upper limit. 0 dB full scale is the upper limit. Beyond that, we don't have any more digital bits to encode with, and so it becomes undefined and we get clipping. This little drawing at the bottom is kind of a visual representation of the unlimited headroom that we've got in the floating point, but then we have to get it out that little pipe at the end. So if we don't turn our level down to where the amplitude will fit through that pipe, we're going to cut off anything else above and below that. So that would be our clipping. Where do we put the limiters? Right before the amplifier. It should always be the last thing at the edge of your device. It should be after all of your, there should be nothing beyond it. Essentially, you can put a meter hung off of there, but you don't want to put any kind of object that would affect level. You don't want to have a level control or an EQ or anything after it. Those should all be prior to the limiter. Limiter is the end of chain right before the amplifier. In Tesira, the 28 dBu equates to 0 dBFS full scale. It's a backstop to prevent clipping over AVB. If it was a Dante hop, you could do that right before your Dante output block. It's the same thing. It prevents clipping over Dante. Tesira uses the look-ahead limiter, infinite to 1 ratio, and you can think of it as a very, it'll take that and just apply a very fast level adjustment to that peak so that it maintains the waveform before it leaves the box without truncating it. And we'll see an actual image of that in a minute. If you don't use the limit, you can clip at the digital interface. The blue lines are an AVB hop out to the amplifier. That's your digital interface. What'll happen if you're exceeding that floating point limit down here at the bottom of the screen, this dashed line is 0 dBFS. In floating point, we don't care about that. We can go on up. We can have plus 40 on the meter and it's happy. It's in the red, but it's, it maintains the waveform just fine. When we try to squash it through that smaller pipe though, it cuts off the top and bottom of those waves. And once those are cut off, we can never recover them. So we want to use the limiter to prevent cutting that top and bottom off. Here is a 500 hertz tone played out in Tesira. This is it on the tone generator. It's playing at 20. So we're not clipping. We're nice and quiet. We're hitting it. So this is at 1.0. That's a digital full scale up and down. So we're down not quite half, not quite 6 dB down. If we were 19, we'd be 6 dB down. Now we're going to boost it up. We'll go up to 25 on that tone generator. Not clipping. We're a sine wave. We've got a 3 dB crest factor. This is an RMS scale here, so we're minus 3 dB FS. Looking at the full wave in Audacity, we can see peak to peak, it's right up to full scale, and we see the 500 hertz in the spectrogram. Nice and clean. As soon as we boost that up beyond 25, we hit 25.1. If we don't have a limiter in there, we're going to start clipping. And when we start to clip, we get harmonics. So this is, I've pushed it up from 25 to 36. So we're really pushing it. So we can clearly see the truncated wave. We've smashed them through that smaller pipe, and we've cut the tops and bottoms off of those sine waves. And we get a lot of harmonic distortion. They're odd order harmonics. Usually when they talk about like tape saturation and tube saturation in electronics, those are even order harmonics, and they're musically pleasing. Odd order harmonics that you get in digital just sound awful. They're harsh and grating. And here we can see total harmonic distortion has gone, whoops, scrolled the wrong way. From a clean signal, almost unmeasurable, to the distorted signal, 32% distortion. So huge amount of distortion. We've also gone up to -6 dBFS RMS. So we're actually exceeding digital. We're just kind of this uncorrelated stuff. So you're getting weird output. And these are the harmonics seen in the spectrogram. So we're just getting these additional steady tones that are overtones of the 500 hertz. If I engage a limiter, so in that previous shot I had the limiter bypassed. If I engage a limiter, that waveform is rebuilt. It just turns it down. It applies a level control, and I don't get any deformation of this. I'm seeing a slight harmonic there. That's due to the release time, short release time. If I extend that release time, we'll actually see that harmonic fall away. But that's the release time that I've put in all the presets that are in the Tesira software. But still, your harmonic distortion is very small, and that's going to only be while you're hitting that limiter that hard. So here we're going to look at it in a video. This will actually show this onset. So we're going to start out signal muted. We'll unmute the signal. We'll see this is a Room EQ wizard doing the measurement. We'll see the peak get defined at 500 hertz. It takes a minute for the samples to refine. It's pinning it down. See a nice clean signal. We'll run this up. We've got the limiter bypassed, so we just went up to 25.1. We get the harmonics appearing. So as soon as you exceed digital 0, we see harmonics come in. We'll run this right up to 36. And we can see these harmonics. Now we need to save things. So let's put that limiter in. And we'll engage the limiter. We'll take it out of bypass in a second here. And so it has changed the level on that signal coming out. It's basically it's using its look ahead feature, and it is keeping the waveform from being distorted on the way out. And we'll see this drop down. And then I'm going to change the release time out to 150 milliseconds and watch the harmonic distortion, the THD level. We're at 0.12. So massively better. So that is a quick illustration of limiters in action. That's just why you want to use them. They're a huge benefit to your system. Pause that guy. So if we don't have a limiter in there, we get distortion. We can have undefined data basically going out across the network. Results anytime there's a peak, they hit the snare drum or whatever, we get that distortion through the driver. And so what was nice sounding audio gets all crunchy and awful sounding. And if we do this long enough, and if we are playing it loud enough, well, then we can cause catastrophic failure in the device. You can actually cause the voice coil to overexert or melt down. So it can be pretty bad. All right. That is, oh yes, almost forgot. 8021X, network security. Tesira and TesiraXEL support 8021X network access management. In Cisco, it's .1x and Extreme Networks net login. We can do this on Tesira Control. We can do it on AVB and VoIP. If you're doing it on AVB and Extreme, We've got some tech notes on it, but you have to set up, you can't use dynamic VLANs for it, but you can do ABB over it. It requires authentication of a device. It needs it to be known, not only on a MAC address level, but like not as a family of products, but actually as a registered user on the network, so that you can authenticate with a authentication server before you're allowed on the network. So while we're not encrypting ABB, we are able to guarantee that anyone on the network is someone who's allowed. All right, our final deep dive. We're going to get into some network topologies real fast here. Network ports, we have 2 ports on this device. They are an ABB switch. We've got daisy chain as the default mode, so we can just chain amplifiers together. It also supports single cable mode. When it's in that mode, you just plug in channel 1 or port 1, and you can discover. RSTP allows for redundant signal paths, so we can allow that to route. We can make loops, and it won't break the network. These are the different network modes. You can see more about these within our support.biamp.com by searching for Excel. It'll walk you through the different configurations, but the daisy chain configuration, separate control and ABB if you need those two to be on different networks, and then redundant ABB. So we've got a primary and a secondary ABB network. When connecting, port 1 is the default port. It always is ABB and control, unless we put it in the separated ABB and control, then port 1 stays ABB, port 2 becomes control. Uplinks, generally you just always want to use port 1 as your initial uplink. If you're going to connect a server IO or a Forte at the end of a daisy chain, you discover with your computer at the amplifier side, not at the server IO side. You'll see the server IO or the Forte, and you won't see any amplifiers because they don't discover across that hop between the server IO, control, and ABB ports. So this mode, all good. If you connect at the other end of the stack, if you were to wire your computer onto the Forte or the server at the bottom of the stack there, you would only see this Forte or server, you wouldn't see the rest of the devices. In daisy chain networks, we've got a few things we can do. We can do kind of a star configuration going out. So we can have our server cores in the middle or a Forte core in the middle going out to amplifiers that are daisy chained in a very variety of racks. We generally, in this application, would say 4 or fewer devices at your racks. It gives you the widest flexibility in your topology. If you go 5 or 6 deep, your total number of hops limits the network diameter. Counting hops, the hop is the wire between devices. And in the end of chain device, we have the 2 ports on the outside of the Excel, and then there's an invisible 3rd port inside where it essentially you've got a switch here and then the wire from the switch connecting to the amplifier. So we add 1 hop at that last device for the hop from the switch to the amp. So in this mode, we would say there were 6 hops in this configuration. How many hops can we support? Traditionally, we've said 9 hops. The reason that we say that is that we don't have control over all the switches and things that are on the network. So we can generally, what we've seen in testing is 200 microseconds between devices. So then we sum them all up and say how many, we've got 125 at the server through a series of 200s and out again 125 on the receive side for playout. Our total worst case scenario 1850, that's under the 2 millisecond latency, and we can synchronize our playout across all endpoints. So we're happy across 9 no matter what. Most applications we can really support 10 to 12 hops because we've seen within switch families they'll vary between 125, 150 to 200 microseconds. If everything is running at 125 milliseconds or microseconds, we can do 15 hops. So 15 wires, 16 devices end to end, and still maintain the 2 millisecond latency window. we don't know the hardware in between for all 15 hops typically. So that would be a scenario that you generally don't want to plan for, because you never know, you know, a switch from manufacturer X might be the 200 microsecond, or it might be 125. You just don't know the performance. And things like fiber transceivers, things like that, can add latency, so it can affect your overall network diameter as well. In the daisy chain mode, we can build a self-contained system here. We've got a control switch, or we can just take the computer right into the amplifier stack. Gives you the ability to plug in and run this whole thing as one big system without needing an AVB switch, an external switch. The danger of this is that we don't have any signal redundancy between those amplifiers. It's you know, if we lose one wire, we lose everything upstream of that. So same application, we've got a Forte on the left stack, a server IO on the right stack. Both are perfectly happy. They're connected single cable mode through the AVB port of each of those devices. We could set it up where we go out and hit a couple of amp racks. Again, our weakest link is that network cable. So if we have a jack that goes bad, or somebody severs a cable, we lose everything downstream of that. So in a perfect world, we've got some redundancy. We'll take a look at just a second here at how we get it. This is just showing the AVB hop count as 12 in this layout. Here we can introduce a bit of redundancy. So we've taken, right now we've got one path to the stage right, and it passes through to stage left. Here we can take this, we've got RSTP enabled on the two switches, or the three switches, and we're doing a ring for those three switches. So if we were to lose the connection between house left and house right, we've still got a return path through front of house to house right. So we're not reliant on one network cable. We still are within the stack of amplifiers. RSTP was added in 3.12 for Tesira, and so it will give us the ability to have a backup network path on the device. RSTP is a network protocol. It's not a Tesira protocol. It looks at the entirety of the network and maps it in each switch. They determine their paths, what the primary and what the secondary paths will be between switches. If a path fails, then it reconverges. It figures out what the backup is. It reapplies it. When it does that, it's got to renegotiate all the paths. It will change the network diameter, most likely, which will change potentially your time between endpoints. So things get renegotiated, so you can have an outage for a few seconds while paths are being reconverged. But it's only a few seconds of outage versus a few hours if somebody chops a cable. So RSTP is definitely a strength. Using RSTP, we can take that stack of amplifiers and loop the bottom one back up to the switch at the top. And now if we lose a jumper between two amplifiers, we still have a path to everything in the rack. Again, we can take that, and we can, at least if we've put that kind of weak, big distributed pair of racks network, we can at least home run that back to the front of house switch. So we've got two paths if we lose one cable. And here's another way to do it, that we've got independent failover paths for the left and the right. We've had some requests for how could you do an analog failover for those two racks. You could set it up that you would have your AVB signal coming in, going through your daisy chained racks, and put a Forte at the bottom of each stack. That Forte would have an analog input mirroring what was being sent to the house left, house right, and then providing that on, you'd have to set up a system file that would accommodate it, but essentially would give you a way to send audio back up. If signal was lost from number one, you have a ducker that brings in signal from the analog input at the bottom. So you become a self-contained stage left rack fed by the analog input, as opposed to taking your feed from the AVB input. So it's a way to provide some analog redundancy if necessary. We also support the primary secondary ports of the server I/O and the server. So on server I/O and server, we create AVB streams on the primary port. They also create a second set of AVB streams on the secondary that are always present, running in parallel with the ones on the primary. We seldom use those, but in this application, we can use those. Take the secondary send out and run a secondary AVB network, and then run that to your amps. So you've got, in the event of a primary network fail, a wire gets cut or a switch dies, the program is running on the secondary. So it's just an instantaneous switchover. There's no muting or anything to happen. And so it's a good resilience. It's even faster recovery than RSTP. All right, that's it for the network modes. Most everything that we've discussed today is encapsulated in some of our articles online. If you go to support.biamp.com and search XEL or TesiraXEL, you can find a link to all of these articles. The Amp Power calculator is found in our tools section. We go through signal path redundancy, software setup, network configurations, all the chassis functions, and talk about the asymmetrical power banks. We also have some system design guides, which give some just some applications with breaking out drawings of how rooms can be laid out, powered with TesiraXEL with different scenarios, and we're always fleshing those out with more and more system design templates. Let's see, I had a question on the hop links between amps and the network for control only. Not sure I totally understand the question. We have AVB and we have control. They can be isolated from one another in the networks. In this case, we are running Tesira control and AVB primary on the primary port, and AVB secondary only on the secondary port. So if we were to lose one of these switches, we would lose the ability to control it, to do mute or level change within a device, but audio continues to flow. We don't lose any of the audio paths. We just lose the ability to do a mute or something until we recover the audio or recover the control path up here. So hopefully that covered that question. All right, and that's it. Ran a bit over. I was hoping to get done in an hour, and I realized I had made way too much material for that. So thank you all for sticking with me. I appreciate everyone for attending today. We do have the PDF of the notes in the handouts. Feel free to grab that. We will be posting the video with commentary online within a few days. We need time to post-process on it and get it up, but you'll get a notification email when that comes due. All right, thank you all very much, and have a great day.